Has any of you ever been using like formal methods or automated proof softwares? Oh, many of you. I found this topic super interesting because when I first read of it, I was like, oh my God, now I'm going to prove the security of everything I've written so far. Then I realized it takes a lot of time and it's very difficult, and most of this stuff doesn't have at all any kind of documentation. So, but I mean, Cornelius works on formal method as a for security and network management, so I believe he will be able to tell me more about this. And in particular, for this talk of today, he will be telling us about verifying properties of iptable's firewall rules. So please give him a big round of applause.
OK, thank you very much. Thank you all for getting up that early and joining my talk. This talk is called Verified Firewall Rule Set Verification. So I think it's best to first refresh our knowledge about firewalls in the first few seconds. So here's a firewall rule set I found on a network-attached storage. It's a Linux IP tables firewall. Let's just walk through that rule set to see what it does. So let's say we have a packet for this box. The packet is given to the input chain, and the box will now walk through all these firewall rules sequentially until it finds a matching rule to know what to do with this packet. Let's just do that for the sake of example, so we all know what firewalls do. So this is the first rule the box will look at. What you see there on your right-hand side is what we call the match condition. It tells you if this rule matches for a packet, this rule matches for all protocols, all source IPs, all destination IPs. So essentially this rule matches everything. And then it will execute this action, which is called DOS protect, which means we jump to the user-defined chain DOS protect, which is down there, and we'll continue our evaluation there. The first rule, let's read the match condition first, looks at ICMP protocol, any source, any destination IP, ICMP type 8, which is an echo request, as we all know, and checks if a certain limit is not exceeded. If this is the case, well, we return to where we came from. Otherwise, we will go to the next rule. It looks at ICMP echo requests again and drops them. So we see a pattern here. Those two rules essentially implement rate limiting. First, if the limit is not exceeded, we can go out of the DOS protect chain. Otherwise, things are dropped here. The same pattern we see here for TCP packets. TCP flags obviously reset flags set there. If a certain limit is exceeded, they will be dropped. Otherwise, we can return. So let's say we get through the DOS protect chain without being dropped. We end up where we came from. The next rule accepts all packets which belong to an established or related connection. Accepting everything that belongs to an established connection is usually considered best practice. Opinions differ on the related match. Well, the interesting question is, how do we get a connection in an established state? Well, this is what most of the rules of a firewall are about. So how do we get in an established state for this firewall? Well, not for SSH packets, they are blocked. Also a lot more TCP ports are blocked. Also a lot more UDP ports are blocked. Finally, the firewall is accepting something. It's accepting all packets with a source IP address in the local 192.168.0 range, and it's dropping everything else. Okay, I hope by now we have refreshed our knowledge about firewalls. So, what's the problem with firewalls? Well, I guess everyone in this room loves open source solutions, so we don't have to care about backdoors in proprietary software. We also don't have to care about grober Unfug such as security made in Germany. We love our open source firewalls, the Linux or BSD firewalls. They are quite good. So what's the main problem? Well, there was a study that looked at real-world enterprise firewalls out there in the wild, and the study found, well, there are no good high-complexity rule sets. So the main problem with firewalls is administrating them, setting them up, which all comes down to configuring the rule set for the firewalls. And, well, a few of you were laughing. That rule set we saw on the slide before was actually quite simple. Just imagine those rule sets get larger. A study repeated this finding a few years later, and it still finds, well, firewalls are still poorly configured, so it's all about the firewall rule sets that, well, if the rule sets get complicated, we make errors. And by no means do I mean that administrators are incompetent. No, thank you very much to all those masters of complexity out there who get our network running. Thank you to the NOC for everything. Thank you for not firewalling us here so we can have more fun. So it's all the configuration of the firewall. So people had the idea, well, let's just write a few tools that check our firewall rule set and tell if the rule set is good. People had that idea, and we looked at the tools that were out there. So we we fed those tools some real-world firewall rule sets, and we found, well, there's essentially no tool out there that understands our real-world firewalls, because have you ever opened man IP tables extensions? Well, then you understand why things can get very complicated there. So, and even if we had a tool that would check our firewall rule set, would we trust that tool? Well, probably not. So, let's do where others failed. Let's try again. Let's try to write a tool to check firewall rule sets. But because we found, well, tools we have so far do not understand our rule set, let's start from the very beginning. Let's first talk about specification and implementation. When we mean implementation, we are usually talking about the code, about our tool. We talk about low-level hacks to increase the performance of our tool, all there on the right-hand side. And this is usually the stuff you don't show to your users. To your users, you show them the specification or the documentation or just the question, what does your tool do? So here to write a tool, we have to answer the question, what is a correct rule set? And for the sake of example for this talk, we will stick to spoofing protection. So our ultimate goal will be a tool that checks if our firewall rule set has spoofing protection. We only have 30 minutes, so let's stick to spoofing protection. But before we can specify what spoofing protection actually means, well, we need to specify what is a firewall. And therefore, we need a model of the packet filtering of IP tables. And that model, you saw the firewall in the beginning, should really, really be expressive so that we can really say, well, this model mirrors reality and we can get all our complex firewalls with all fancy IP tables matching extensions into that model. So we can, in the end, run our tool that checks if we have spoofing protection. We will implement everything in the Isabel theorem prover. Why are we using a theorem prover? Well, you know the good old problem. You look up the documentation of some library you are using, then you look to the implementation and you found, well, the documentation was just plain lying to you because documentation are usually horribly out of date. So in this talk, we want to write an implementation and then prove that the implementation corresponds to the specification. That's why we are using a theorem prover to have a proof in the very end that our code really does what it is specified to do. So the most important thing here is to specify what it should do. So to summarize, what will this talk be about? We will write a verifier for Ruleset and we will verify the verifier itself. So let's get started with step one. We need a model for IP tables before we can specify anything. Okay, we need match expressions. Let's start simple. Let's write down the syntax of match expressions. The syntax is all about how do I write things down. There, let's define a data type, match expression. This data type should be polymorphic over the type '(A), which means this '(A) can be any type. We will call this the primitive, which will be the features IP tables can match on. Let's keep that generic for a moment. So how can a match expression then be constructed? Well, we can match on such a primitive. We can have a match expression that just matches plain anything. We can negate a match expression, or we can combine two match expressions to one larger match expression. There's an example. We are combining two match expressions with this match AND. And there we see in the inner thing, these are the primitives. So those things we keep completely arbitrary. Here we are matching on destination IP and protocol TCP. And again, we will keep all these primitives, the features we can match on, completely generic. This was the syntax, how we can write things down. But what does this mean? Well, so we have to specify the semantics. The semantics is all about what do match expressions mean. Well, match expressions are matching on packets, so we can't specify the semantics without a packet. Let's look at the type signature of the matching semantics first. There it is. Looks a bit intimidating first. Let's look at what we have there. The first parameter of this matches function is a function itself. We call it gamma, and we also call it the primitive matcher, because look at the type of the function. The first parameter is the primitive, some primitive match thing we can match on, for example, source IPs or protocol. The second '(P) is the packet it should match on. By the apostrophe, you see we also have a generic packet model. You can plug in there anything, and it returns a Boolean, true or false. And, well, this function gamma should return true if and only if this primitive match condition matches for a packet. The second parameter for our semantics is a match expression, as we defined it before. Then we give it the packet. We want to know if it matches, and returns true if and only if the packet matches for the match expression. So let's look at the individual rules here. The first rule, straightforward. If we match on the primitive A for a packet P, well, we just ask our primitive matcher if this A matches for packet P. Then the next rule, very straightforward, the match any match expression matches everything. If we have this match not, which means we negate our match expression, and the match and, you may already have guessed it, is just the conjunction of the two match expressions. So now we have defined syntax and semantics of match expressions, so we can match on packets. Now we only need to specify the filtering behavior of IP tables. There it is, quite simple. First of all, what the fuck? So the good news about this is, well, this is really everything we need to know about IP tables packet filtering. It's on one slide. If we have enough time, we could really read it. It's much more concise than the man pages. Well, it just has a few funny symbols on it. Let's try to read it. Everything we have there looks the following. Maybe we can recognize something. P should be the packet the firewall is examining. There we have the gamma again, our primitive matcher, which has encoded all the features IP tables can match on. Then at this position, we have the rule set. The rule set is just a list of rules the firewall is currently examining. S should be the start state. The firewall starts looking at the packet. Usually the firewall in the beginning is undecided about what to do with the packet. And there at the end we have the final state. So in the end the firewall usually makes a decision either to accept or to drop a packet. So let's read the rules. Let's read the simple rule, the skip rule. They are all written with this line, which means everything above the line is the precondition, everything below the line is the conclusion. Here we don't have any precondition, so this rule holds unconditionally. So let's read what this means. There we have it. First of all, this rule looks at the empty rule set, the empty list. So what does a firewall with the empty rule set do? The rule says the start state and the final state are the same. So essentially this rule says for the empty rule set, the firewall does nothing. Not really that hard, but we need to start at some point. Let's look at a quite more complicated rule. Here we also have a precondition. And what we are looking at is a rule set which only consists of one single rule, which has some match condition M, and the action is accept. Our precondition is that we assume that the match condition matches for the packet. Well, what would then happen? The action is accept. What should the firewall do? Well, if we don't have a decision for the packet yet, the action was accept, then we are going to accept it. Okay, also not that hard. And I guess we all agree that this is the behavior of our common firewall. So all the other rules, they actually read pretty similar, and we only have 11 of them. So if we have enough time, it's not that hard to read the slide you were first laughing at. So let's directly jump to the most complicated rule we have there in our rule set. It's called the call return rule. Well, looks a bit complicated. It is. So first, again, we have a rule set with a single rule with some call C there, and our first precondition is this one rule matches, otherwise the firewall wouldn't do anything at all. Then there's the complicated part, the action of the rule. We called it our call C, which means we want to call or jump -J option in IP tables to some user-defined chain. The name of the chain here is generically expressed as C. In the example from the beginning, for example, this C was the name DOS protect. And we also have as a precondition that the chain in the background rule set looks as follows. So we have this capital gamma there of C, which basically means look up in the background rule set of all the user-defined chain how the chain of this rule, how the chain for the chain with the name C looks like. Well, so essentially we get what is in the DOS protect chain for the for the example from the beginning. And here we say, well, it looks the following. First there is RS1, then there's mprime return, and then there is RS2, which means, well, this user-defined chain can look as follows. First, there is an arbitrary part called RS1, an arbitrary amount of rules. Could, for example, be the first ICMP rules we saw in the DOS protect chain. Then there is a rule which has an action of return, and then there can be more arbitrary rules called RS2, can be an arbitrary long list of other rules. Okay, And then we have the next precondition. It says we can process this first part, RS1, without getting a decision. So far we have called to a user-defined chain, have processed a first part of this chain without getting any decision yet. Then there's the next assumption. We have a matching return rule. So what does happen there in IP tables? So we have called to a user-defined chain, we have processed something, didn't get a result, then we got a matching return rule, so we came back to where we started from without any result. And this is what the rule tells us. Well, I know I'm going over those formalisms a bit very fast. I hope a few can follow. First of all, the cool thing about this is really a mathematical specification. It's not an implementation. And we can see that we can specify the behavior, for example, of calling to and returning from user-defined chain without a call stack. So this is really just a specification, not an implementation. It's not executable, but hopefully it tells quite clear what the firewall does. Well, anyway, if I already lost you, I hope you can join now, because there's the question, why are we doing all this formalism? Well, let's get a bit more applied. Now with every slide we have, we will get more applied, and we will now use this formalism to actually do something useful with it. Now we just have specified the filtering behavior of a firewall. Okay, let's specify more. Let's read this formula. There on your left-hand side, you have behavior of a firewall. Then we have if and only if, and on the right-hand side again, behavior of a firewall. So this says left-hand side and right-hand side are equal. Okay, where's the difference? The difference here is this f. F is a function which takes a rule set and transforms it to another rule set. So what could this function f possibly do? Well, we said the behavior of those firewalls are equal. So it means that this function f takes a rule set, transforms it to a different rule set, but it didn't change the behavior of the firewall. So for example, f could be a function that improves the performance of your rule set, and you could safely run this function on your rule set because, well, there the formula says f doesn't change the behavior of your firewall. You can safely deploy it to production. And we have implemented several such f functions. A very simple example, we can remove all the logging rules. Our semantics only cares about packet filtering. Logging doesn't influence that in IP tables. So if we remove all the logging rules, the behavior of the firewall stays the same. Okay, simple example. We also can do more. We can unfold all calls to and returns from user-defined chains. So after we have run this function, well, the firewall will be a long list of rules which will all be processed sequentially. There's no more jumping around, which is a cool thing. Unfortunately, the match conditions will get quite complicated for that rule set. But again, we can normalize these match conditions to simpler ones. So in the end, we will have a firewall which is just a long list of simple rules. There is no jumping around, and the actions are either accept or drop in the end. So we can essentially simplify our firewall, and the formula says this simplification doesn't change the packet filtering behavior at all. So we can safely run this. Okay, let's look at more things. We implemented our semantics in ternary logic. In Boolean logic, we either have true or false. In ternary logic, we have true, false, and unknown. Well, what can we do with it? Well, cool stuff. Let's first read this formula. Let's see what we have there in the middle. In the middle, we have a set. We have a set of packets, and the condition for this packet is they are accepted by the firewall. You start in an undecided state, and in the end, you're accepting it. So there in the middle, it says we have the set of all packets accepted by the firewall. Well, we can specify that. As theoretical computer scientists, we believe in specification. We have specified the set of all packets accepted by the firewall. Quite cool. Well, I guess as hackers, we don't believe in just such a set specification, which is standing just out there in the void, having no connection to reality. You can't even execute that set. No, as hackers, we also believe in running code. And this is what we have there in the sets above and below. Above, we have an under approximation, which is essentially a stricter version of the firewall. And there it's important that we embedded the whole thing in ternary logic, because it's quite impossible to implement all the matching features you have in IP tables in an analysis tool. And I'm not aware of any tool that implements the full set, because, well, the NetFilter team also adds new features with many releases. So here we have an approximation embedded in ternary logic. And, well, we have proven that this is a sound approximation, which makes the firewall stricter. So basically, this firewall may accept less packets than the original firewall, and on the set on the bottom, we get an over-approximation, which essentially makes the firewall more permissive. This firewall may accept more packets than the original firewall, and the important thing here is, well, those are executable, and well, the reality or the specification, what we want is in the middle, and we have executable code around the reality, so to say. And well, we will use these things all in the background now, because now we can execute the whole thing and we can safely approximate something if we run into some features we don't understand because we have embedded the whole thing in ternary logic. So essentially, we have now a sound approximation where we can say, well, there's some match expression in somewhere in the firewall we don't understand, the result there is unknown, and the whole thing will be safely approximated according to what you want. Do you want to be stricter or more permissive? So I said I will explain you how we get spoofing protection in the end. Let's look at spoofing protection. Let's first specify what spoofing protection is. Let's say we have an IP assignment there. ETH0 belongs to the IP range 192.168.0/24. So what does spoofing protection mean? It means for any IP packet that enters ETH0, the source IP must be in this 192.168 IP range. So let's specify that. Again, we are looking at a set, and we have seen that before. We require that in the set, these are the packets accepted by the firewall. There's an additional constraint about the packet. The packet should come from the interface ETH0. And just like before, we are looking at the packet, but not the complete packet. We only look at the source IP. So this big set expression on your left is essentially the set of all packets accepted by the firewall coming from ETH0, but only their source IP. Well, and what should the set fulfill that the whole firewall implements spoofing protection? Well, all these source IPs should be in the valid range of that interface. I guess we can all now agree that this specifies spoofing protection for that particular example. Let's generalize that. Let's say we require this for all the interfaces we have in our system, and now we have specified spoofing protection. Okay, again, we have specified it. I guess we all agree that this is spoofing protection. What can we do with the specification? Well, we wrote an algorithm. An algorithm, you only give this IP assignment as above and the rule set, and if the algorithm returns true, you definitely have spoofing protection in your firewall. And let me point out the cool thing about it. There you see this arbitrary gamma. Arbitrary in mathematics always means, well, it's all quantified. What does this all quantified gamma mean? Gamma was the set of all matching features our firewall model supports. Here it's arbitrary. So our algorithm can tell if you have spoofing protection for any magic IP tables match condition you may have in your firewall. Even if the NetFilter team decides to implement a new cool matching feature in the future, maybe they don't know yet that they will implement that feature. Here the specification says, well, this algorithm will correctly understand it and check if you have spoofing protection anyway, even if there is some unknown cool future feature in it. And I think that's a pretty cool specification there that we have about the algorithm. So it essentially says we understand all possible match conditions you can ever use in your firewall. Well, so what about the specification? Well, you know, with normal specifications, well, they are quite imprecise and not really tell you what the algorithm does. This is a mathematical specification. It's concise, it's really precise, and it tells you exactly what the algorithm gives to you. What else about usual specification? Well, very often they lie to you, they have some implicit assumptions, they don't tell you, you have to call them in a special way, but they didn't document it. Well, not in this case. We have a formal proof that our algorithm really fulfills this condition, so there is no implicit assumption somewhere. This specification will never lie to you. And also for some other documentations, you always know that the documentation is usually quite outdated, especially for particular projects. Well, here we have a machine verifiable proof. You can run that proof on your computer. You don't have to reconstruct it by hand. You can give the proof to your computer and tell your computer to recheck the proof at any time. So you can check at all the time if this specification is still what the algorithm provides you. So this specification will never be outdated, and I claim, well, this is probably the best way to document your code, to prove it correctly. It will never be outdated. It's really precise what it does. It doesn't have any hidden assumptions, and it will definitely not lie to you. So, I said we have executable code. Well, this looks like a lot of formula. How does the executable code look like? Well, we wrote the whole thing in Isabelle, proved it, and well, once we got executable code, we can export it to different languages. Here we choose Haskell, and you can really run that algorithm on your machine. You don't need Isabelle or any theorem prover as a backend. It's a standalone program. Here you can see how you can call it. You just feed your IP table safe dump into the tool. Then you supply the IP assignment, as we saw on the slide before, or probably generated by ifconfig or IP address show. And the tool will just automatically run. It doesn't need any additional input. You don't have to prove anything by hand. It will just check if you have spoofing protection on your firewall. So there we have it. We have a verified tool to verify that you have spoofing protection on your firewall. And because I'm running out of time, I just want to show you a short outlook, what else we have in our verified tool set there. Well, probably you have seen on the slide before, how big was this firewall? 4,800 rules, quite large. I guess this firewall rule set now hit the 5,000 rules, and we had the question, well, by the way, who is allowed to set up SSH connections with whom in a 5,000 rules firewall rule set? Well, there is the answer. All these ranges you see there, internal servers, INET, they essentially correspond to the complete IPv4 address range. I just gave it symbolic names here because, well, those ranges are really split up, maybe non-continuous, because there are so many exceptions in there, but they are all clustered together. And we have proven a few things about this graph. It's the complete IPv4 address range. All these IP addresses that are grouped together, for example, in the servers or internal group, really have the same access right. And this is the best possible solution you can get for this question, because you cannot compress this any further. You can't get a clearer or better answer to that. Well, you may ask, why do we have there on the left INET and INET prime? Well, because of a typo in the firewall, which is now fixed. Well, it's pretty clear in the graph that you don't want two internets there, and you can really see the bugs there. And what was really interesting, essentially for us, we looked at the long list of servers there and internal there, and really verified that all these IPs for the servers are the machines which should be accessible by SSH. The internal ones are the ones which should not be accessible by SSH. And well, for a 5,000 rule set, you can see that there are a lot more funny exceptions which have funny access rights, which we probably also should look at. Okay, that's it. Thank you for your attention. Well, it would be really, really great if you have some firewall rule sets lying around and would want to donate them for research. Would be really, really happy. And of course, everything we are doing here is not only fully verified, but also completely open source. You can get everything. Thank you for your attention. I guess we have a few minutes left for questions. Thank you.
So yeah, just line up in front of the microphones right here and here. I think there is one. There you go.
So have you done any work, or are you aware of any work that involves studying firewall rule sets of multiple cooperating firewalls?
Short
or
answer.
Is this possible with your...
At the moment, no, but there is other work in research which already claims to have solved this problem. And they did, but they have a very limited firewall model. What we can do with our tool, you can give us an IP tables safe dump with all the complex features you have in the firewall. We can simplify it either to an over or under approximation, which will create a much more simpler firewall rule set. And this simple firewall rule set is then actually understood by some tools which have been developed in academia.
Okay, thank you.
We can pre-process, but we don't have yet incorporated further analysis in a fully verified manner.
Hi, thank you for the talk. It was very well done, and I would like to get more involved in like formal methods and proof theories and stuff like that. But I have trouble knowing where to start. I was wondering if you had some insight into what resources would be good to get started with programming in Isabelle or Coke or even Idris, things like that?
So first you should look at the theorem prover at your choice. I prefer Isabelle. If you're more from the programming community, you will probably enjoy Coq more. It depends a lot on personal choice and everything. If you're a student at TU Munich, you should definitely go to Tobias Nipkoff's great courses, because there we have the Isabelle group directly. And if you want to get started with Isabelle, there's the book Concrete Semantics by Tobias Nipkoff and Gerwin Klein, and I hope I didn't miss another author, which is, I guess, freely available. You can also buy it, and all the examples in the book should be included in the default Isabelle distribution, so that's the easiest way to get started. Download the complete Isabelle package, look at the book. It runs usually on your system. You don't have to compile any additional packets, and get started with the book.
Okay, thank you very much.
We're running out of time, but Hey, we're running out of time, so there is time for one last question from the Signal Angel.
Yes. On the IRC, they would like to know what's the time complexity of the algorithm.
The runtime complexity? Well, bad news. This pre-processing can blow up to exponentially many rules. In theory. In practice, we looked at a lot of firewalls. And this exponential complexity is sort of exponential in how fucked up you manage to call your user-defined chains. So usually you do that by hand or semi-automated, so it doesn't blow up that much. The worst thing, to tell you real numbers, I saw is it was about a 500-rule firewall based on a Firewall setup, which was really, really quiet. Well, it triggered that a lot, and also when we rewrite IP address ranges to non-negated zero range, which can also blow up a lot. The worst blow-up we ever saw was from 5,000 rules to 20,000 rules, which is still very good handleable by a computer, because afterwards, basically all our algorithms are mostly polynomial time, if not even linear. To tell you real numbers, this took about 1 minute of pre-processing for 5,000 rules and then about 1 second per interface, and this took less than 2 minutes, also for 5,000 rules. So you can really run those things on your computer.
Cool, thanks.